So let's start with just thinking, we'll think about this algorithm in the simplest way, and this is the not parallel version of this. So don't anybody run back to your blog and post it and say, this is what compute shader code looks like. This is the not parallel version of it. Somebody's going to do it, though. You know I'm right. So basically, this is what I just talked about, right? For all pixels, get their intensity, and then divide that at the end by the number of pixels, and that's the average luminance. So that's just to make sure we're all talking about the same problem. So here's the first example of this reduction compute code, right? So we're going to have a group shared int, which is the total we have so far. Another group shared int, which is the count, how many pixels we have, okay? And then we're basically going to, using different threads, we're going to load that up, calculate the luminance, basically cast it to a uint there. Then we do this interlocked add, okay? So here we're doing memory protection there, right? We're going to add that to the count. Well, we're going to increment the count by 1, right? We've processed another thread. We're going to do the interlocked add to the total, saying, hey, here's the most recent luminance I got. Let's add that to the total. Synchronized thread group that says, hey, let's wait until everybody's finished. I've just repeated that on the top of the next slide, so we just have some continuous flow control. So let's repeat that. We're just going to wait till everybody finishes, and then at the end, we only need the first thread to go and say, hey, give me the average. So that's okay. It's parallel. We can do better. How can we do better? Well, basically, what I've done with this code is I said, hey, everybody go off and do everything in parallel and then go stand in one line. It's like what they make us do at lunch here, right? There's all these tables. Please go stand in that first table, right? And you're looking at all the other tables like, I want to eat. So these guys want to eat, basically. We can do much better. So let's look at another code example of how to do better. So here, what we're going to do is break this across 32. We're going to create 32 lunch lines, as it were. So now we have 32 of these totals. We have an array of that, 32 of these counts. We're going to do the same thing that we did before, but now instead of making everybody wait in one line, with those interlocked adds, they get to wait in 32 lines. Okay. Everything's the same. Then at the end, that first thread's just going to go across and do that last sort of summing up. So this sort of, pyramidization, this is a pretty common construct in parallel programming. I'm sure you've all seen it before, and this seems really trivial. And of course, there's a trade-off between how many of these lunch lines do you create, based on your memory and things like that. But it gets the idea across. So this is obviously a super trivial example of the kinds of things we're enabling with compute. The compute stuff is documented in the November SDK. You can do much more interesting stuff. Just in the context of this talk, I just wanted to make it concrete about, we're basically enabling the constructs you know and love in parallel programming. So again, protected reads and writes. There's different levels of locking that you can do. Of course, the tighter the lock, the more of a performance trade-off that is. There's nothing new. So you can sort of read about all those things. The idea, getting back to the summary, is this enables much more general algorithms to be moved to the GPU to take advantage of the increases in GPU performance. It's this transparent parallel processing model. It does have full cross-vendor support. We've been working with all the IHVs to develop this compute shader. So they're all in support of it. They all helped us design it. We didn't design it in a vacuum. This is also exciting. It's going to run on DirectX 10 and 10.1 hardware using shader model 4.0 parts. With these features, this will require an updated driver. So with the multi-threading before, remember I said, hey, it's going to work just as is. This one actually, it'll work on your 10 hardware, but you have to get an updated driver for that. And again, on the newer hardware, with the newer shader model, you'll have even more functionality. But we're trying to make it, give it the broadest reach possible. And so again, we're targeting older hardware and newer hardware. How are we doing for? I talked too fast. Okay, so we're at the end now. Sorry, we're at the end now. There's just a plethora of other features that we've put into Direct3D 11 that we're not going to talk about today. Some of them are, so addressable stream out. That means we already had stream out functionality, but we've increased the stream output buffers to 4, and you can change all the stream output buffers to be multi-element if you want. Coverage is now a pixel shader input. What else do we have going on here? Pull model for attribute evaluation. That's the ability to evaluate attributes within a pixel, somewhere on a sort of predefined multi-sample grid. Let's see. There's improved Gather4 support. We now support multi-component textures with Gather4. There's now required 8 bits of subtextual and submip filtering precision. So again, we've tightened the spec up there. Optional double support, increased resources, things like that. So a whole bunch of new functionality coming online. So for Direct3D 11, the summary here is that, again, I want everybody to understand it's just a superset of 10 and 10.1. It adds support for features like multi-threading, like tessellation, like the compute shader. You know, the fastest way to move to 11 is actually to start becoming familiar with 10 and 10.1 if you're not already. This will be available on Windows Vista and Windows 7. It'll also run, as I mentioned before, on down-level hardware. So multi-threading and compute, 10 and 10.1. You can also get to 9 via that 10 level 9 that I talked about earlier. Probably not going to give you screaming performance, but depending on the scenario, it might be useful. Full functionality for some features, like tessellation, that will require 11 hardware. So when can I get it? So the bits, of course, the DLLs, the system DLLs, are already on that snazzy hardware.